So today's lecture involves a fair amount of problem solving, but half the problems will be very similar to problems that you'll have already done, in which case I'm just going to use slides because you already basically know all the main theory. Maybe there will be like one extra little step or something. But anytime that we actually have a problem that involves new material or concepts, I'll still write by hand the way that I've been doing. So let's get into lecture 6. Briefly, let's recap acid and base constants. So let's say you have the classic weak acid, acetic acid in water, which forms the conjugate base acetate via this reaction here. You should all become very comfortable with this type of acid dissociation reaction. It has a K value. It's rather small, which agrees with this being a weak acid. That small K means very little of our reactant actually dissociates into products. And the larger a K value, the stronger the acid or the base, because larger K implies more product is being formed. Strong acids and bases have K values that are at least 100, if not 1,000,000. Now once that conjugate base is formed, there are two reactions that it can participate in. One, it could react with water like a base would, in which case it will take a proton from the water, reform acetic acid, and leave behind hydroxide. In this case, we can calculate the Kb value by taking Kw and dividing by Ka, and we get an even smaller K value than the acetic acid has, indicating that its conjugate base is also weak, which led us to the conclusion that weak acids are conjugate to weak bases, contrary to the phrase that you may have learned once before. Now the other reaction that acetate can participate in is just finding a proton in solution and reforming acetic acid. This is literally just rewriting the first reaction, but in reverse. And we learned that when we write an equilibrium backwards, we just take the original K value and invert it, which gives us a very large value of 5.6 times 10 to the positive 4. That large K tells us that this is a very favorable reaction. And that explains why acetic acid is so weak in the first place. It can only dissociate so much before these two products start finding each other and reacting back to reform the acetic acid, because it's so favorable for the backwards reaction to occur. The only reason it doesn't always happen is because there is such a small concentration of these two produced in the first place that they don't find each other in solution that frequently. But when they do find each other, it's very favorable that they react together. That will be a very important point for later today. Now the other concept that we learned about was how to calculate the pH of a solution, and we gave particular focus to calculating the pH of a weak acid solution. And we used this as our example, a 1.0 molar solution of acetic acid, and we calculated its pH by first writing the acid dissociation equilibrium and setting up an ice table, where we had initial concentrations of 1.0 molar of acid and effectively no product at all before anything happens. Then everything changes by the same number, minus x plus x plus x, giving us these final equilibrium concentrations, which we would then plug into the K expression and set that equal to 1.8 times 10 to the minus 5. At this point, we would need to use the quadratic formula to solve for this, but we do have this small x approximation that lets us sidestep the quadratic formula. And that approximation states that if our K value is at least 1,000 times less than the initial concentration of the species, we can assume that we can ignore the plus or minus x term. In other words, that change there will be so small compared to that initial concentration that we don't need to really consider it when we solve for x. And so applying that logic to this problem, well, that K value is definitely 1,000 times smaller than 1, and so we can ignore that minus x term there and just plug in 1.0 in the denominator. On the other hand, that K value is definitely larger than 0, so we can't ignore these plus x terms, and so we'll still have x squared in the numerator. But as we saw when we did this problem, that did not require the quadratic formula to solve for. And so from there we just go through the math and we follow these 4 steps. And we're not going to write out all the math because we already did that last lecture, plus we're going to see a couple of examples of this type of work anyways as we go through today. So today I'll start by describing how we could change the pH of a solution via neutralization. So let's start by writing that term down. Neutralization. Which is what happens when we add an acid to a base and at least one of them is strong. So let's write this. If a strong acid is added to a base, if a strong acid is added to a base, and it doesn't matter if that base is weak or strong because we've already said that at least the acid is strong. The base is protonated to conjugate acid. Base protonated to conjugate acid. In other words, the reaction that's going to occur is H plus from the strong acid, so let's write that in parentheses, from the strong acid. And let's emphasize that the reason I'm writing H plus as opposed to the whole acid is because the only important part of a strong acid is that H plus. Because we know that something like HCl isn't really HCl in water. It 100% dissociates into protons, and Cl-, which we covered last lecture, is an ineffectively weak base that does nothing in solution. So it's really the H plus that matters for what we're discussing now. So that proton is released by the strong acid, and then it finds a base. And these two react to form BH+, the conjugate acid of that base. Notice it is a forward arrow. This reaction goes to completion, and that is due to this reaction having a very large K. And we covered that logic in the recap when I showed acetate ion reacting with a proton has a very large K. So that basically when these two species find each other, the reaction is very favorable, and it does go effectively to completion. So we'll write that note. Reaction essentially goes to completion. Because K of neutralization is large. Because K of neutralization is large. And it's very important that you know this, that a neutralization reaction does not reach equilibrium, it goes to completion. We'll be seeing a lot of neutralization reactions in the future. And conversely, we can neutralize an acid with a strong base. So I'll write something similar to what we already wrote. A strong base fully deprotonates an acid. And it doesn't matter if that acid is strong or weak, just so long as the base reacting with it is at least strong. So strong base fully deprotonates an acid. And so the reaction looks like this. Hydroxide ions from the strong base, Sb for short, meet the acid, and they react completely. The acid is deprotonated, leaving behind conjugate base, and that proton was taken by the hydroxide to form water. And so when you do these kinds of neutralization reactions, and you convert these bases or acids into their conjugate acids and bases, you can bet that's going to disturb your pH. But there are solutions that can resist those disturbances, and we call these solutions buffer solutions, which is the major focal point for the rest of today's lecture. And so buffers regulate the pH of solutions. Some important buffer examples, well, we have biological buffers in our bodies. They regulate the pH of our blood and make sure that we stay safe and healthy. There's medicinal buffers, because medicines only work over a certain pH range, and so we need to keep that pH relatively stable. There are aquatic buffers that keep aquatic life from ending when acid rain enters these marine biospheres. So, future biochemists, doctors, environmental scientists, buffers are important. And even if you're in the minority of students who isn't in one of those three tracks, buffers are still important. So what are they? Well, we will end this video with a quick definition. Buffers Significant amounts of a weak acid and base that are conjugate to each other. Significant amounts of a weak acid and base that are conjugate to each other. And when we say significant amounts, we're saying that the amount of acid and base in this mixture are within 10 times each other. So, within 10 times each other. And if it's not clear what I mean by that, hopefully it will become more clear as we learn more about buffers through examples that we'll be covering through the rest of the lecture.